In lecture 2, we're going to be looking at the various macromolecules that makes up the living organism. There are proteins, there are carbohydrates, there are lipids, and nucleic acids. We're going to look at the chemical properties and composition of each of these macromolecules, as well as their functions and role in the living organism. Before we talk about macromolecules, we have to go through some basic chemistry first. These are chemistry related to a biological system. It should be similar to the kind of stuff that you're learning in your chemistry course as well. So it will be a refresher for some of you. So matter is anything that takes up space and has mass. And matter can be solid, such as ice. It could be a liquid, such as water, or it could be gas, such as water vapor. And of course, they can cycle through the different states of matter depending on the temperature change, for example. And all matter is composed of elements. Elements. What are elements? Elements are substances that cannot be broken down into other substances. Okay, so you cannot take oxygen, for example. You cannot take oxygen and break it down into something else. Okay, oxygen is an element. Okay, unlike things like water. Okay, water is not an element because water can be broken down into oxygen and hydrogen. Okay, so if something cannot be chemically broken down further, then we call it an element. Right? And all matter is composed of one or more elements. Atom. An atom is the smallest unit of an element. Okay, so if you talk about oxygen again, the oxygen gas is made up of many oxygen atoms. Okay, and it is the smallest unit of an element that still retains the same chemical and physical property as the element itself. So the individual oxygen atom is going to behave exactly the same as the oxygen gas itself. The atom is made up of subatomic particles. So there are three types of subatomic particles. In the center of the atom, we call that the nucleus. There are going to be neutrons, which does not carry a charge, and there are going to be positively charged protons. Okay, so P for protons and P for positive. So the protons and the neutrons will clump together to form this thing in the center called the nucleus. Revolving around the nucleus are going to be negatively charged particles called electrons. Okay, and they would go around in various shells. The farther away they are from the nucleus, the more energy they would have. So together, the nucleus and the electrons, they make up an atom. All the elements that have been discovered so far in the universe are put on this periodic table. So if you can find something on the periodic table, then you know it is an element. And if you cannot find it, then it's not an element. For example, copper, right? Is copper an element? So copper, the symbol is Cu. And because you can find copper on the periodic table, then you know this is an element. And just to reiterate, if something is an element, it means you cannot chemically break it down into something smaller. Okay? Is sugar an element? Okay, so sugar, and you have to go through the symbols, and you wouldn't be able to find sugar on it. And in fact, sugar is not an element. Sugar, the chemical formula is C6. H12O6. Right, this is one type of sugar, and this is made up of many different elements. Okay, so there is carbon, right, in it. There is hydrogen in it, and then there is oxygen in it. Okay, so because it's made up of many different elements, it itself is not an element. Okay. What are the basic elements of life? Okay, even though the human body is obviously very complex, but it turns out 96% of the human body is composed of just 4 elements. So of the 118 elements found on the periodic table, 96% of the human body is composed of just 4 of those elements. So the main elements that makes up the body include carbon, nitrogen, oxygen, and hydrogen. Okay. In fact, 65% of the body is made up of oxygen, 18% is made of carbon, 10% hydrogen, 3% nitrogen, and then the rest, the remaining 4%, is going to be other elements. So these other elements are only going to exist in the body in trace amount, in small quantities, and in fact we want them to be in relatively a small quantity, because it turns out if you overdose on these quantities, or if you have a deficiency in this trace element, they would often result in some kind of disease. So examples of trace elements, and again trace elements are the elements that are only required in small amount in the body, and they make up the 4%, the remaining 4% of the body. Some example of these include zinc. Okay, zinc is important for defense system, for example. There is calcium. You probably know calcium is good for your bones. It makes them strong. But we also need a bit of calcium in order to move our muscle. There is iodine. Iodine is required from your thyroid gland to make hormones that would then regulate your metabolism. There is magnesium, which is also needed for muscle contraction. So what happens is, if you have iodine deficiency, for example, if you don't have enough iodine in your diet, then your thyroid gland can get big, okay? And that's something called goiter. And we don't really have that problem in North America, the iodine deficiency, because our table salt actually has iodine in it, and the reason is to exactly prevent iodine deficiency. And you know, if you live in some other parts of the world where they don't have iodinized salt, then you would get your iodine from eating seafood, for example, shell seafood, or just simply fish. They are pretty rich in iodine. Okay. Calcium deficiency, you probably know that if you don't have enough calcium, then your bones would get quite weak, and that could lead to osteoporosis. Okay, so this is the bones with osteoporosis. You can see is very porous. There's a lot of holes in it, and of course that makes them quite weak. There are something called isotopes. So atoms of the same elements will always have the same number of protons. Okay, we cannot change the number of protons. By changing the number of protons, you actually will change the element. So if I look at carbon, okay, so all the carbon atoms are going to have 6 protons in their nucleus. Okay, however, the atoms do not necessarily have the same number of neutrons, even though they belong to the same element. So there are something called carbon 12. Okay, in carbon 12, they would have 6 protons and 6 neutrons. However, in carbon 13, you would have 6 protons. Remember, protons don't change for the same element, but you would now have 7 neutrons. Okay, so this is a little bit heavier compared to the carbon 12. Don't worry about how to calculate these numbers. That your chemistry teacher will teach you that later. What you have to know for this course is that atoms of the same elements with different number of neutrons, we call them isotopes. Okay, so some isotopes are unstable and they break down naturally on their own. We call them radioactive isotopes, and those radioactive isotopes are particularly important for many applications that we have. For example, if there is a fossil that has been dug up, not fossil, but like old skeleton, and you want to know how old it is, and you can use carbon dating to figure that out. Your smoke detector actually has radioactive isotopes in it in order for it to work, and we can also use radioactive isotopes to detect brain tumors in imaging techniques, and we can use it to even treat some forms of tumors, such as those in the thyroid, for example. So radioactive isotopes are quite important for many reasons. So ions, what are ions? Atoms of the same elements can gain or lose electrons to become ions. Let's go to say oxygen, for example. Right? Oxygen normally has 8 electrons. Okay, so it would be able to gain 2 electrons. Okay, and if it gained 2 electrons, we put 2 negative, and that would make it negatively charged. Okay, when something is negatively charged, we call it an anion. Something like calcium, right? Calcium can lose 2 electrons to become more stable, and when it loses electron, it will become positively charged. We call that cation. Okay, so there's a positive here, there's a T here. That's how you can remember cation are positively charged and anions are negatively charged. How many electrons they gain or lose depends on which column of the periodic table they belong to, and again, that's something you will learn in your chemistry class. What you do need to know is that ions are charged elements or particles, and for the biological system, there are many important ions that exist within bodily fluids. We typically call them electrolytes, right? So on a hot summer day, if you are running outside and you want to replenish your fluid, right? You would drink something like sport drinks, right? Like Gatorade. And in Gatorade, there are a lot of electrolytes. So there are potassium in it, there are sodium in it, right? Maybe a little bit of magnesium. All these are electrolytes that we need in the body. And in fact, a lot of these things are part of the trace elements, right? We're gonna need these trace elements in small quantity for normal bodily functions. So we talked about atoms and how they are the smallest unit of elements, and so the atoms themselves can actually combine in fixed proportions, fixed ratio to form molecules. Okay, we sort of talked about this. Remember, I gave you an example of sugar, which is C6H12O6. So that means to make a sugar molecule, you would need 6 carbon, 12 hydrogen, and 6 oxygen. And these ratios are going to be fixed. Okay, so here is another example. We have sodium. Sodium is an element. So if you're able to virtually zoom into this, then you will see the individual sodium atom. Okay, and sodium is actually quite explosive. Okay, if you put this chunk into like a tub of water, that could create a really big explosion, and you could potentially hurt yourself. There's chlorine gas here, okay, and chlorine, if you zoom in, you will see the individual chlorine atoms, and chlorine is really poisonous. Okay, it's something that they use to make gas grenades, right, during the World War II, and you definitely don't want to be sniffing that stuff. However, sodium and chlorine can combine in 1-to-1 ratio, right, to form sodium chloride. So sodium chloride is NaCl, which is table salt. Okay, so table salt is a molecule. Okay, it contains 2 different types of element in this case, 2 different types of atom in this case. So once the atoms combine together to form a compound, then the properties of the compound is very different than the individual elements that makes it up. Right? Like I said, sodium is explosive, chlorine is poisonous, but sodium chloride we put on our fries all the time, and it's quite safe to do so. Right? So just to summarize it for you, elements, right? Everything found in the periodic table is considered as elements, and they make up everything in the world, make up all the matter. And the smallest unit of element is atom. Okay, atoms. Elements can combine, right, together to form a compound, and the smallest unit of compound is a molecule. Okay, so here we have sodium element, chlorine element forming the sodium chloride compound. Okay, and on a molecular level, on an atom level, we have sodium atom combining with chlorine atoms forming sodium chloride molecules. So how do atoms come together to form molecules? Well, there are 2 ways to do it. We can have a metal combining with a non-metal. Okay, so metal atoms, they tend to lose electrons to become more stable, whereas non-metal, they tend to gain electron to become more stable. So when you have a metal and a non-metal coming together, the metal will transfer the electron to the non-metal, and in doing so, they form something called an ionic bond. Okay, so these are quite strong. The bonds are quite strong, the ionic bonds, because they are held together through electrostatic attraction. So when the sodium lose the electron, they become positively charged cation, and when the chlorine gain the electron, they become negatively charged anion, and positive are attracted to negative, creating this strong ionic bond. Okay. On the other hand, we can have a non-metal and non-metal coming together. So in non-metal and non-metal, rather than having a transfer of electron, they have a sharing of electron. So here we have the oxygen sharing the electrons with the hydrogen, and the sharing of electron creates what's called a covalent bond. Okay, covalent bond. Molecules that contain carbons are known as organic molecules, and many biologically important molecules are actually organic. So glucose, which is the sugar that we use to burn as fuels, that contains a carbon. I keep on mentioning C6H12O6. That is the formula for glucose, a type of sugar, and there are 6 carbons in it. We call that organic molecule. Proteins are organic molecule. Not all organic molecules are found in biological system, or at least not found in high quantity. So for example, our clothing is polyester. That's not something we found in the body. It's in fact a synthetic polymer. It's considered as organic molecule because it contains carbon. Methane gas is CH4. We do make a little bit of methane gas. Animals, they make a little bit of methane gas, but there are a lot of methane gas in greenhouse emission, for example. Not everything that has carbon is considered as organic. There are actually a few exceptions, and the exceptions are listed here. Okay, carbon monoxide, the poisonous gas that could kill you, is containing carbon, but we don't consider that as organic molecule. Okay, carbon dioxide is something that we breathe out. We don't consider as organic molecule, and cyanide is poisonous, and that's also not organic. So for the most part, besides these exceptions, anything that has carbon is going to be considered as organic molecules, and not all organic molecules are biologically important. Some we use it in various applications. Water is, of course, very important. More than 70% of our body is made up of water. And so we're going to look at the properties of water and try to explain why it is the way it is. Okay, so first of all, water is a molecule, and the formula for water is H2O. That means there are 2 hydrogen atoms, shown here in white, and 1 oxygen atom. So it is considered as covalent molecule, a covalent bond, right? Because it contains nonmetals sharing electrons together. However, the sharing of the electron is not even here. Okay, it's like, you know, if you have 2 kids and then you brought them a new PlayStation or something, and you say you guys gotta share it. Okay, but then the older one is always playing it a little bit more. So even though they're sharing it, but it's not an even sharing. There is an uneven sharing of the electron in this case. So which atom gets the electron a little bit more depends on something called electronegativity. Okay, and that's something you can look up on the periodic table. But for us, we only have to know that comparing oxygen to hydrogen, oxygen is the one that is going to be more electronegative. So the oxygen is like the older brother, okay? Even though it's sharing the electron with the hydrogen, but it's kind of hogging it to itself. So when you look at an oxygen molecule, a water molecule rather, okay, when you look at a water molecule, okay, the oxygen that is more electronegative will pull the electron towards itself a little bit more. Okay, so as a molecule overall, the oxygen will be slightly negative, and the hydrogen, on the other hand, is going to be slightly positive. Not all molecules are going to have this a type of uneven sharing. Okay, in other molecules, the electronegativity are more similar between the atoms, and so they have even sharing. And if is an uneven sharing, then the molecule will be partly negative on one side and partly positive on the other side, and that makes the molecule polar. Okay, so water is a polar molecule. Here in the diagram, you can see this oxygen is slightly negative, and therefore it is going to be attracted to the slightly positive hydrogen on another water molecule. Okay, same thing, right? We have the positive here attracted to the negative, and so on and so forth. Okay, so these water molecules are going to be attracted to each other like magnets. Okay, magnets, the opposite poles attract. So similarly, for the molecules, if they have opposite charges, they are going to be attracted to each other. Because water molecules are polar, that makes water an excellent solvent. It's able to dissolve many ionic compounds. And what is a solvent? In case you don't know, a solvent is something, it's typically a liquid that will be dissolving something. Okay, so if you think about Kool-Aid, Kool-Aid is going to be the solute here, and the water is going to be the solvent. Okay, and when you mix it together, you get a solution. Okay, so in the body, we have a lot of water. Like I said, 70% of the body is water, and a lot of the electrolytes, a lot of the ions that we need are going to be dissolved in those water. Okay. So water, because it's polar, is able to dissolve other polar substances or ionic substances. Okay, so salt is, for example, sodium chloride. I told you the sodium is positively charged and the chlorine is negatively charged. So what happens when you dissolve it in water is that the water is going to be able to dissociate the sodium from the chlorine. Because water itself is polar, and let me just draw that for you again. There is a water molecule here, and this is slightly negative, this is slightly positive. So when you put sodium chloride into water, the positive hydrogen will now surround the negative chlorine. Okay, if you don't remember why chlorine is negative, just go back a couple slides earlier and see that it becomes negative because it received the electrons from the sodium. So when you put sodium chloride in the water, then the hydrogen in the water molecule will surround the negative chlorine. Okay, shown in this picture. For the sodium, on the other hand, sodium is positively charged, so then the oxygen part of the water molecule, which is negative, will be surrounding the sodium. Okay, and so you are able to dissolve table salt in water, and that's pretty much the case for other ionic compounds as well. So substances that can be dissolved in water, we call them hydrophilic. Okay, hydro means water, philic means loving. So hydrophilic means water loving. Okay, so anything that can be dissolved in water, we say they are hydrophilic. The opposite of hydrophilic is hydrophobic. Okay, phobic is hating, right? If you have phobia, you really hate or are afraid of something, right? So hydrophobic means they are water hating. These are typically non-polar molecules. Okay, they do not have uneven sharing of electrons, and therefore they don't have a positive or negative side to it. Okay? They are just neutral, as there's no uneven distribution of charges, and those do not mix well with water. Okay, they don't dissolve in water. An excellent example of that would be oil. Right? We know oil don't mix with water, and these molecules, we call them hydrophobic. Knowing whether something is hydrophilic or hydrophobic will help us predict how they behave within the body, because the body is, again, 70% water, right? So hydrophobic molecules are going to behave very differently than hydrophilic water in these aqueous or watery environment. A concept related to solution is pH. The pH scale measures the concentration of hydrogen ions. Okay, so the square bracket means concentration, and we are measuring the concentration of H+. What's H+? It's basically a hydrogen atom. Okay, so hydrogen atom is going to have one proton in the middle and one electrons on the shell. When it loses the electron, essentially you have just the proton left. Okay, so a hydrogen ion is basically just a proton. So sometimes you hear people say there's a high concentration of proton. They are basically referring to H plus. So if a solution has high concentration of H plus, then it's going to have a lower pH, which means it is going to be more acidic. On the other hand, if it has lower concentration of H plus, then it will have a higher pH, and that is going to be less acidic, or we say more basic. Okay, so what's acidic and what's basic? Like, what does that mean, right? Typically, acidic stuff are things that are going to be sour, right? So you think of like lemon. We have acid in the stomach that's going to be sour. That's the hydrochloric acid in the stomach. Tomatoes, sour. Okay, they are going to be corrosive. Especially if it's really low pH, they are going to be quite corrosive. On the other hand, basic stuff are typically bitter in taste. Okay, they are also corrosive. Okay, and that includes things like baking soda, household cleaning products, oven cleaners, and sodium hydroxides. These are all bleach. These are all examples of base. Okay, so our blood pH has to be about 7.4. Okay, so 7 is neutral. 7 is like a pure water is going to be neutral at 7, and our blood is a little bit higher than neutral, 7.4, so slightly basic, and we cannot deviate from that too much because it would actually destroy and interfere with a lot of the protein's function, as we will learn later on in the lecture. So more on that. Like I said, 7.4 is the norm, and the maximum amount you can deviate is down to 7.35 and 7.45. And if it goes below 7.35, there's too much acid, so we call that acidosis. Okay, osis is too much of something in the blood. On the other hand, if it goes greater than 7.45, then there's too much base, too much alkaline in the blood. Then we call that alkalosis. Right? So there are mechanisms to try to bring these back to normal, and typically speaking, they do a pretty good job. And the respiratory system and the urinary system will help to maintain the pH balance. Your breathing pattern might change. If you have too much H+, you can put some of that in the urine. And there's also something called a buffer system in the within the blood itself. The buffer system we have is something called the bicarbonate buffer system, the H2CO3. So this buffer system will help you maintain a normal pH of 7.4. Okay, so if it goes too high, it's going to be able to supply H plus to bring it back down, and if the pH gets too low, the buffer system is able to remove the excess H plus and bring the pH back to 7.4. So that's it for this video. In the next video, we will be looking at the main macromolecules of the body.